Great pleasure to be here. Thank you very much for the invitation. After the fairly machine learning heavy talks this morning, I will be talking about some applications of machine learning in the field of cosmology. And the topic that I've chosen, from inference to discovery with AI, I will go through 3 steps: inference, information, and discovery. And I will motivate why AI is really at the basis of a revolution in cosmological physics, and as an example of the revolution that it's causing in the physical sciences in general. Before I do that, let me first give you a 4-slide crash course in cosmology, because I know not everyone here is a cosmologist. So the playground of cosmological physics is this. You're here today. This cone represents everything that you see when you look out into the sky. The farther away you see, the more distant into the past you see. And so the farther down on this cone you're looking. What you see when you do that is listed on the left, roughly corresponds to the ordering in which things appear on your past light cone. And what that covers, a few milestones in cosmological physics are written on the right. One point or one locus on this light cone is of particular interest, other than where we are today at the top. And that's the base of the light cone, inside this part here, inside of your past light cone. You think of it as a disk. That's because I'm not showing you all 4 dimensions here. I'm expressing a dimension in this representation. All right, and many of the milestones that you will have heard of, if you have any interest in cosmology whatsoever, are listed there on the right. So that disk there at the bottom really are the initial conditions that could be the product of a very early universe process. Often we think about this as an inflating period of the universe that produces the initial conditions. And one of the key aspects of the problem is that all you really need to know, in addition to all the physics, but the other thing you need to know to predict anything that happens, anything that you might ever observe, is encoded in that disk at the bottom, because then the world lines that go up intersect your past light cone and determine what you will see. And we believe that there are quantum processes in the very early universe that create these quantum fluctuations, the initial conditions at the bottom there. All right. So these initial conditions there at the base of the past light cone, these curvature perturbations, actually are in 3D. So this ball of fluctuations determines everything that happens in the universe throughout all of history. Everything can be predicted based on that plus physics. So your world line starts in the middle.
Sorry.
Oh, it's working. Your world line starts in the middle. Okay, and so when you're looking out into the universe, you're basically seeing some processed version of these initial conditions there. And so, for example, when we made a map of the cosmic microwave background, that's the most direct probe of these curvature perturbations in the early universe. And so when people say that we look back to the Big Bang, that's what people mean. Okay, so cosmology is all about taking those initial conditions. And by the way, this is a simulation that has the right statistical properties based on what we know from our observations of the cosmic microwave background, galaxy distribution on the sky, etc. All of these observables that I had on the first slide. And we take those initial conditions, and then using physics, we can then predict and with a few unknown quantities, the so-called cosmological parameters that quantify the statistics of these initial conditions and basically the contents of the universe. We can predict everything that we see on our past light cone, and that might be, some galaxies, observations of the cosmic microwave background, polarization, all these different things, these complicated data objects, right? So that's the forward problem, and cosmological inference is just turning that arrow around. So we want to go from all of these quite complicated data objects on the right. Galaxies are pretty complicated, but everything that we can observe about the universe, and go back to these initial conditions and those parameters. So that's the big problem, and it's a fascinating problem, because a lot of different physics at different scales interact. If you want to do this in the way that I sketched here. And we have no shortage of data. So that's the other important point. That's why cosmology, we live in a special time as far as cosmology is concerned, because we are still in an exponential growth phase as far as cosmological data is concerned. And we have been in an exponential growth phase actually for the last at least 30 years. And it's still going. It's just a subset of important past surveys and current and ongoing and somewhat future surveys on this slide. So all these data sets that are filling in this past light cone with observations, they range from simple to complex. They're relatively simple when you look on the very large scale. So I'm showing an image of the cosmic microwave background. That's very directly related. This is an actual image, so that's only a small amount of translation needs to be done to turn this into the initial condition, into a slice of these initial conditions. But when you zoom in, you start seeing structure at all kinds of different scales, and I switch over to galaxy surveys at some stage. So right on the top right there, that's roughly the scale of current galaxy surveys. And I keep zooming in, and eventually get to the stage where there's a single galaxy there at the bottom, which is where we live. So this is all of cosmic structure on one slide. And because it's such a multi-scale problem, that leads to this being quite complex. And it turns out there's a scale hierarchy here in terms of complexity. On the largest scales, we have perturbative results that are very accurate, but on the smallest scales, everything becomes nonlinear, and that's the challenge, because the largest number of bits of information are also on these smallest scales. So that's really the problem that we're trying to solve. So how do we deal with this complexity on small scales? Actually, I'm showing a simulation here, but in this simulation, you see some very heavy clusters or nodes of this cosmic web that forms under gravitational collapse of these small perturbations, initial perturbations. How do we deal with that? And until not so long ago, honestly, the best tool we had to deal with that was just to do this. To just smooth it all away so that we only had to deal with the large scale, which we could deal with perturbatively, okay? And this is sort of the pre-ML era, which is not that long ago in this field. All right, but even now, I mean, I would say, we had a conversation yesterday. Somebody asked me, so the Euclid spacecraft that you may have heard of, recently launched, currently entering its performance validation phase, one of these upcoming large surveys, charting our local universe. Most of the first results of the Euclid survey, at least as currently planned, will not use any machine learning, in terms of the physical information that's extracted. So that's how not long ago it is. All right. So let me talk about inference. And in fact, I will take a point. I know that there are many ML. All of you are ML experts. Some of you are physics, or most of you are actually also physics experts. Some of you are astrophysics and cosmology experts. Some of you may be statisticians, but maybe not everyone is familiar with statistics. So I'll give you a very, very quick, brief introduction to statistics as well. Okay. So here is how you would do what I would call explicit inference. Okay, this is how you compare the data to the theory. You write down an explicit physical and stochastic model of your data, given your parameters theta, and this is called the likelihood. Okay, that's that object there. This P of D given theta. You get your data, You specify a prior on your parameter space saying, what do I know about my parameters now before I've taken the data? Then you write down the posterior using this formula. Posterior is the thing on the left that tells you, what do I know about the parameters now that I have the data, given the data? And then you explore that function on the left for fixed data as a function of the parameters, and then you're done. And that's the recipe for comparing data with theory. But what if you don't have a likelihood or not a good likelihood? A lot of the current analyses assume that the likelihood has a Gaussian form or some other simple form. But for many of the data sets that I even just mentioned, that's just simply not a good approximation. Certainly not on these small scales, for example. All right, so that seems problematic. Well, what if we don't even have a closed form way of writing down the prior? A lot of people think about the parameters maybe, as these cosmological parameters I mentioned, then typically you assume some very broad, not very informative prior. But what if the thing you want to reconstruct, might be might be an object that is produced by a generative model. So some more complicated data object where you don't know how to write down your signal model because it's quite complicated already. So you might have your signal be complicated and intractable with no closed form. You may also have your data and your noise model be intractable and complicated with no closed form. So this explicit inference approach is limited in that sense. So then even if you can write this down, it can also be complicated to explore or sample the posterior. And I know whereof I speak, been building hierarchical Bayesian models for quite a while now with many parameters and sampling techniques and so forth. And it's kind of an art form all of itself. Okay, so what we want is we want freedom. To succeed, we need more freedom than a traditional likelihood approach can provide. We want freedom to make our physical model anything we want, because that's ultimately, and I'm sort of anticipating the end of the talk, this is ultimately going to be the limiting factor. We want our physical model to be anything we want to choose. We don't want to be restricted by the stats. We want freedom, this is also going to be important, to project, summarize, cut, mask, or whatever we need to do to the data to make the data look like our model, if you want to do parameter fitting, in any way we want. And those two are just difficult to achieve if you have to write down closed form, explicit forms of your likelihood. But, and this is the way out, simulating the data is often much easier than deriving an accurate likelihood as an explicit form. So the question is, can we analyze data if all we can do is simulate it? And the answer is pretty much yes. And this has been a major shift, let's say, over the last 5 years. Now, this is maybe not so much news to some people in the audience here, and some of the talks in the parallel sessions, for example, gave already some examples of this kind of approach. It turns out that you don't have to write down the likelihood; you can just represent it implicitly through simulations. So as long as you can draw data from your likelihood for a particular model, you can do inference. And I'll give you a very simple example. I'll just go through that very quickly, and I challenge you, just keep a running count of the number of times that we have to evaluate a likelihood or even a prior, okay, as I do this. So here's a very simple example. If you don't understand Bayesian statistics, you will understand it in roughly 2 minutes. All right, so here's the easiest diagram to explain Bayesian statistics. You have parameters, in this case only one on one axis, data on the other axis, okay? So if you have a prior, let's say we take a uniform prior over the parameters, just for illustration. All right, we just we generate possible theory values from that prior. So we have given you a random sample. Okay, so now for each one of those, we will now use the likelihood or our model to generate possible data for those values of the parameters. So here we'll generate a few at every point. Actually also in between, but I didn't draw them all because otherwise this would not be visible. All right, so here's a whole bunch of simulations from those prior parameter values. Okay, and now I'm going to take some data. So the data will fall somewhere here on this data axis. All right, so this is a sample of the joint distribution of parameters and model parameters, model parameters and data. Now I'm going to draw some actual data. It's the green line, and all I now have to do is just basically look at that. This is the conditional density here of parameters given that data, and that's the posterior, and then you're done. So here, this is not actually how we do this, but in order to do this with discrete samples, we have to assume a little epsilon around this. This is not necessary in practice. Other methods are more powerful. This is just an example. But okay, let's count, basically histogram those points that are selected by the data. There they are. Let's count them. Here they are. Look at this. The true theta, by the way, that I used to generate the data set was that vertical line. So it's covered by this posterior distribution. And so here's the posterior. Okay, so that's Bayesian inference in a nutshell. Every Bayesian inference works the same way. It's just in higher dimension. So, and with different methods. How many likelihood evaluations do we need? None. We simulated from the likelihood. How many prior evaluations do we need? None. We simulated from the prior, right? So you don't need to write down forms. Okay. So this is what I call implicit inference. I'm trying to, this is for me the natural way to call this. When your likelihood and or your prior are not explicitly specified in terms of some probability distribution, but implicit in, it could be simulations. That's often the case in physical sciences, but it could be generative models, could be a neural networks generating something. It could be labeled data that you find somewhere. Okay, it just happens to have data parameter pairs that exist somehow. Those could define your model, and then you can do inference based on that. Okay, so it's very general, and various forms and special cases of this are called likelihood-free inference. You might have heard that. I don't like it particularly because there is still a likelihood. It's just implicit, not explicit. Or simulation-based inference, which is often accurate but doesn't need to be actual simulations. Or sometimes called approximate Bayesian computation. That's kind of the old nomenclature. That's because they're in the example I gave you because there was an epsilon. That's why it's called approximate, but it doesn't have to be. Okay, so now machine learning takes us the rest of the way to actual, making this actually practical, not just one parameter, one data point. And what this teaches us is that we can, or the insight there is that we can recast inference problems, like, as optimization problems. And once you do that, we now know how to optimize stuff. It's called neural networks and all the beautiful work that we heard this morning, right? So we just parameterize the solution using a neural network in some way. Oh, first of all, we write down a loss that defines the problem. So that's, in some sense, that's kind of that's the way we program that, right? We just have to think about the loss that, when optimized, gives us the answer that we want. We parameterize the solution using a neural network, we minimize, and then hopefully you have the ability to validate that model as well. Okay, so I'll give you a bunch of examples for this program now. By the way, so in astrophysics and cosmology, this has really started, I would say, a revolution. There now problems that would have been considered, like people would have laughed at you if you told them that you could do this 5 years ago, are now basically done as a matter of course. For example, automated finding of summary statistics that extract information from your data. I'll go into this a bit more later. Or computing posteriors or likelihoods, or using prior information for intractable models. Fitting hydro simulations to data, like putting full computational hydro simulations to data. I know people would have thought you were crazy if you were suggesting that. Now there are many papers already that are doing that. I'm not going to give you examples here now because I wanted to talk about more recent stuff. That's how it is. Like it's already, that's old hat now. And one thing I'll talk about more later is also when we get to the discovery part, I'm going to mention evidence calculation. So that's evidence in Bayesian statistics as a way to compare models probabilistically. Okay. And a bunch of references here to earlier papers that really started this. Okay. So the first example, variational Bayes. We heard about variational Monte Carlo. This is a little bit different, but related. So the idea is variational Bayes in general is you define a parameterized family of distributions, and you hope that the posterior distribution that you're after for your parameters is somehow in that family, or at least approximately. And then you define a distance at some level. It's not a distance, but a loss between your between this family and the true likelihood. I wrote likelihood, but it could be the posterior. And I already gave it away. So what's new is that we can write down much more general families now than we could before because we have neural ways of encoding them. So, for example, when using a neural density estimator, this is Delphi, which so I'm writing down this loss here. This is the Calvert-Lambda divergence between two probability distributions. Try to estimate the true one, and you have your family that's parameterized by some parameters, weights, for example, W, the neural family, and then you approximate this integral by a sum over your training set, and then you minimize this as a function of your weights. And that will give you an approximation, in this case, of the posterior, of the likelihood of your data. So just as an example out of astrophysics, but there are now many, this is a strong gravitational lensing example. So strong gravitational lensing is a relatively tricky inference problem where you're observing some background galaxies as it's magnified and distorted through the gravitational potential of a foreground object. And so here are examples of what those distorted lenses look like. And what you want to do is two things. You want to reconstruct the image of the background galaxy. You also want to learn the parameters of the foreground potential. And this can be, like I said, it's quite tricky. This stuff often, like this used to take days and weeks of computation on computers for a single object. Now, just implementing this program that I just told you about by writing down a likelihood family for the parameters and showing it lots of examples generated through forward simulations, you can then write down these posteriors. And they are amortized posteriors in the sense that if you've done this once over a large enough set of examples, you can just show data to this network and it immediately spits out the posterior. Okay, without any sampling, no Markov chain Monte Carlo, nothing. Okay, so here's just one example for what, just to show you what it looks like. In particular, I'm showing this because this is the case where there are clearly multimodal solutions. So these are not very simple likelihoods. They're quite complicated. You've got curve degeneracies and things like that. And it just still works, and even with a fairly large number of parameters. So here's just some examples of what these sources look like, and you can then validate this by generating lots of these examples and checking that the true parameters, when you rank them, correspond to the inferred parameters in the right fraction of the time. And this is the two different versions. So ignore the blue curve. The orange curve is the one that works. You want the correspondence to be basically the identity on this diagram. Okay. All right. So this variational Bayes approach, or density estimation likelihood for inference, as it's also often called, gives you a full posterior distribution over all these parameters. Could be cosmological parameters. I chose a different example here. But representing high-dimensional posterior distributions gets difficult even when you're using neural density families. simply because large dimensional spaces are exponentially large, and so if you're parameterizing distributions over that, it gets exponentially hard. And so how do we handle high dimensional problems where you have, you know, rather than 5 or 6 or 10 parameters, maybe you have 100,000 parameters. One way to do that is to simplify the problem. So the way that you would do it in the old way is you would write down your full model, your full forward model, you would write down explicit likelihood functions. You would then have to figure out how to sample the parameters given the data. This is often quite, requires a lot of skill in terms of getting these samplers to work, Hamiltonian Monte Carlo and various other things. In this case, and then at the end, once you've done it, typically what you show in a paper is just two-dimensional marginals, like 1 or 2-dimensional marginals. So you, at the end, you integrate through everything and you just show whatever you fits on a page, okay? So you can simplify the problem and just go to the end result directly without going through the intermediate step of having this high-dimensional posterior, or even necessarily the samples, but we'll see. So this is an approach which is really very simple. It turns out you can write down a minimization problem. So just the standard mean squared error loss that you all know. If you train that, you just write this loss, and if you write the training data, the distribution over training data and parameters as the joint distribution of data and parameters like this, turns out when you vary that, we find out what solves this loss, what minimizes this loss. It turns out to be the posterior mean. Okay, so just simply by training a network with these joint draws from parameters and data, and just minimizing mean squared error means you can compute posterior means. Okay, so it turns out that, by the way, a lot of the weird behavior of networks at the edges of your training data set and so forth that people think are mysterious are explained by thinking of the output of the network as the posterior mean rather than some kind of magical estimate. Okay. Okay, but then there's no reason to stop there. If you want to also know the uncertainty, you know, typically you would like to compute at the very least the variance of the posterior distribution. Okay, so you write down a loss that computes that does that. Okay, you define a second network, G, function of the data. You have a quartic loss like this, and that G will, once trained, will give you the variance of your posterior variance. Okay, and this is for the 1D marginals, but you can do this for 2D marginals, and you know, compute little covariance matrices, and without ever sampling anything, just directly. If you don't just want to have a sort of mean and variance of location and scale, you can then do. It turns out, you know, you can also go directly to the marginalized distributions by just writing down the KL loss, the variational loss that I had earlier, only in those dimensions where you want to see it, like in pairs of dimensions, for example, for 2D marginals. So you can just skip the high dimensional problem altogether and go directly to the thing that you want to put in the paper. Okay. This solves the curse of dimensionality for these problems. Here's an example for order a few 100,000 parameters. If you're hunting for primordial gravitational waves in the cosmic microwave background, you're looking for the amplitude of primordial tensor modes. They show up in a particular mode of the polarization in the cosmic microwave background called B modes. So this is the truth. Once you add, the problem is that unfortunately from inside the galaxy, what we actually see looks more like that. Because it turns out the dust in the galaxy is also polarized and has this filamentary structure and kind of complicated. But if you consider every single pixel here as a parameter and you apply these Bowman networks to it, you just compute posterior means and variances for each one of those parameters, you get what's on the right. So this is for magnetohide. Play some tricks for generating enough simulations here. I don't want to go into that. This is some wavelet scattering moments. But we generate a whole bunch of examples of these crazy foregrounds, add them to a whole bunch of examples, this signature of primordial gravitational waves. And then given a particular input, this is the posterior means. So all of the pixels, and these are the posterior variances. You can see very clearly that this is a non-Gaussian problem with the foregrounds. And so, for example, the variance is a function of position on this map, which would not happen if you did this in the Gaussian approximation. You get the same variance everywhere. And the posterior means also do the right thing. You can then validate this. Turns out, just by looking at the posterior means and variances and rescaling under simulations, and it gives you the right answer. Yes.
Maybe a very naive question from the last slide.
Yes.
But I'm looking at the second pane and the first pane.
Yes.
And I'm wondering how the information is in the second pane to reconstruct the first pane.
Right. Yeah. So the reason why you don't see this in there is because the scale is very different. So the signal is very small underneath all of this foreground. So the only way that this can happen is because the foreground really has such different morphology from the signal. And it's only using that. So it's actually using less than what we'll have in the observations, because the observations also have some color information. This is just monochromatic. So we actually have more information. But here, the network is just looking at this and going, oh, these kind of weird filaments, they don't look like that. So can't be right. And it just ruins that. So you just look at this, there's some right here in the background, maybe you can see some of the signals. So it's still in there. But really the only thing that the network is using is the morphological difference between the noise and the signal. Okay. Right. Okay. Yes.
You turned a sampling problem into an optimization problem.
Yeah.
Can you say again, how multidimensional is that optimization problem?
The optimization, I mean, in this particular case, the optimization problem was high dimensional. The output, we were just basically estimated all of those means at the same time, but you could do each one individually. I mean, you could just split up because each one is just the best estimate. So for this particular case, it's the optimization problem is still high dimensional. Yeah, right. But doesn't seem to be particularly hard. It's using a UNet architecture. Yeah. Okay, so what if you're not satisfied with getting two-dimensional, or one-dimensional marginals, or these approximations, or two-dimensional marginals? What if you actually want to have information about all the complicated interactions of the different degrees of freedom of the thing you want to infer? So everyone here, I'm sure, has heard of score-based diffusion. We can probably skip over the explanation on the slide. Score-based diffusion is a technique that is used for generative models, where you learn how to generate models based on first generating a very noisy version of the model, and then learning a set of denoisers that then, when you run it in reverse, give you samples. It's described on the slide. I'm running late, so I'm going to skip to the answer. So what we want to achieve here, the example problem I'm showing you here, is the first time that we're reconstructing initial conditions from fully non-linear simulations of the final state. So final state dark matter in this particular case. So we're starting in the early universe. We simulate dark matter forward, producing this cosmic web and so forth, and then we're going to be generating initial conditions using a conditional diffusion model. Okay. So here's the final state. This is a output from an n-body simulation on BIND on a 128 cubed grid. And here are samples of these initial conditions. This is this little piece of the ball that I showed you earlier. Okay, and these are different samples. I'm showing a few of them just for illustration. We can generate. These are posterior samples for 128 cubed parameters. So this is order million parameters. Here are slices of these reconstructions, so you can look at them more carefully. Here's the present day redshift 0 input, where you can see the cosmic web. The true, or yeah, this is the output of the simulation, the input into the inference. This is the true initial condition slice that gave rise to this, and here's one sample of the reconstruction. You can clearly see the correspondence of the different structures. Again, this is a problem that will be infeasible using any other technique. And we could, because we have samples, we can also measure the uncertainties in the reconstruction. And you can see very nicely that the uncertainties are large in the overdense regions. And there are good physical reasons for that. I'm happy to explain if you have questions. Okay. All right, so here's the measure for the accuracy of the reconstructions of this. This shows the spatial power spectrum. Gets reconstructed extremely accurately. It does much better than the best case linear filter that you could apply to this problem. And the thing down there is just a zoomed in version of the top plot showing that it's very, very accurate down to the Nyquist scale of this problem. All right. Given the time, I'm probably going to have to go very quickly over this. For people that are interested in information, if you want to extract information from data, the most complete way of doing that is to actually get the likelihood surface or its gradient. Those are sufficient statistics if you have them everywhere. And the covariance and the gradient of the likelihood with respect to the parameters is called the Fisher score. And the covariance of that is the Fisher information, which is a fundamental object in asymptotic statistics and information geometry. It's the metric of information geometry, and is used extremely widely, at least in astrophysics, but also in other areas for experimental design and planning, okay, for predicting how much information a proposed observation has about some interesting parameters. So in order to compute those, though, you have to have likelihoods, right? But what if you don't have them? What if you're in a situation that we just described earlier? Well, it turns out you can compute them using neural networks. You just have to write down the right optimization problem. It turns out that the right optimization problem to write down is this thing there. It's the kind of the Shannon information for based on it turns so there's an interesting fact that emerges from this that I don't have time to discuss, but it turns out that by writing down a Gaussian likelihood for the output of the network and writing down the Gaussian form of the Fisher information and computing that of the output of the network, you can compute the Fisher information of whatever goes into the network, even though that likelihood is completely unknown. I can show you the proof of that if you like. It's a little bit bizarre, but yeah. Okay, so let me show you how it works. You can test this for simple cases. For example, this is a simple inference of variance, where you know what the answer is for the Fisher information. And any linear summary would give you much, much less information. And it turns out that using this approach gives you also gives you the correct summary, and you can use it for inference. Okay, let me skip over this Gaussianization property. You can apply it to fields. This works well in higher dimensions. Again, in this case, we know what the true information is, and we find the network approaches that as we train. And this is for non-Gaussian fields. So we can now compute Fisher information for any object that you give us, the score and the Fisher information matrix, including graphs, for example. It doesn't matter, like any data that you can stick into a neural network and that can produce an output, because we can do the calculation by defining this optimization in terms of the Fisher information. We can compute Fisher information for any object. So we've used this for graphs, for example. Okay, I need to conclude. Here, if you're computing Fisher information, here's a new way of estimating it with fewer simulations. All right, the last thing I want to talk about. Okay, maybe you can ask me about how to use this for model comparison. Okay, but so there's more stuff here, but I'm apparently at the end of my talk times.
All right, let's thank our speaker.